Alright, hello, this is a follow-up video to one that we previously did. Now we're looking at how second derivatives affect the shape of a graph of a function. Alright. So, now we'll look at what f double prime, or the second derivative, tells us about the function. So, one way of thinking about it is it tells us the rate of change of f, since the second derivative is the derivative of f prime. So f prime is the rate of change of f, so f double prime would be the rate of change of that, the rate of change of the rate of change. So for example, if you wanted to know if you're increasing, not just increasing, but increasing at a decreasing rate, you'd look at the second derivative. So we're increasing, but maybe we're kind of slowing our increasing rate, something like that. When we see this graphically, this is what's called the concavity of a graph, and that's one of the main topics we want to explore here. So kind of in some informal way, it measures the curviness of a graph, in the sense that if the graph of f lies above all its tangents on an interval, it's called concave upward on the interval, and if it lies below all of its tangents, then it's called concave downward. So what that would look like, just kind of generically, let's say we've got something like, I don't know, a nice function like that. Here, this would be about where it's concave up. And I'm out of space, so let me just say concave up. And out here, concave up. And what we said about, in terms of the tangents, if you look, tangent line, tangent line, tangent line, tangent line, it's always below that red part of it. The graph of the function. So concave up there. And then if you look at something like, I don't know, this part, there would be concave down. And again, if we had, our tangent lines don't seem real well at the yellow probably, but they're all above. So the graph, so the function lies below. The graph lies below all of its tangents. Well, that's one way of thinking about it, but probably not a super helpful way in terms of making computations or things like that. So we'll talk about that in just a second. One thing I want to warn you about is that this is completely independent from increasing and decreasing behavior. So throw 4 examples at you real quick. I could have something that's increasing and concave up. I could have something that's increasing and concave down. You have something that's decreasing and concave up. Interest of space here. Start doing some abbreviating. I could have something that's decreasing and concave down. The whole point is that the increasing or decreasing has nothing to do with it. Alright, so it describes the concavity, second derivative describes concavity in this sense. If the second derivative is positive, then the graph is concave upward. If the second derivative is negative on an interval, then the graph is concave downward on that interval. Alright, so the way we're going to tackle this, we're going to try to figure it out is, just like we did with increasing and decreasing behavior, we're going to try to find values where the second derivative is 0, or not defined. For increasing and decreasing, we looked at where the first derivative is 0, not defined. So now we're looking at the second derivative. If it's continuous, then between those numbers we have either exclusively its second derivative is positive or it is negative. So in between those numbers, the graph is either concave up, concave down. And if it's not continuous, you just look at the continuous parts, keeping in mind that where the continuity fails, we might have you know, a point to keep in mind, because across that the behavior might change. So these points where the graph of a function where the concavity changes, these are called inflection points. So they're kind of like local extrema. Local extrema would be where you change from increasing to decreasing behavior, or decreasing to increasing, and inflection points would be where you change from concave up to concave down, or vice versa. So like I said, we're going to kind of have the same plan of attack that we did, a very similar plan of attack that we had for first derivative stuff, looking for local extrema. So what I want to do is I want to find zeros of the second derivative. And this is one that we've seen before in a different video, so let me just say recall. F prime, the derivative is negative 3x squared plus 3 over x squared plus 1 squared. So, second derivative is going to be, using the quotient rule, I've got negative 6x times x squared plus 1 squared minus negative 3x squared plus 3 times 2 x squared plus 1, oh no, times the derivative of the inside, which was 2x. All of that over x squared plus 1 squared, so that's to the fourth. Now one thing I can do real quick to help out, I've got a common factor here. I can lose one of those in the denominator. And so this ends up being negative 6x times x squared plus 1 minus 4x times negative 3x squared plus 3 all over x squared plus 1 cubed. Again, we're going to note that this is defined everywhere, so we don't have any problems where it doesn't exist. We're strictly looking for zeros. So the second derivative is, flash back here, I've got negative 6x cubed minus 6x plus 12x cubed minus 12x all over x squared plus 1 cubed. Okay, so what am I going to do here? I've got negative 6x cubed plus 12x cubed, so I've got 6x cubed minus 18x and so that's going to be 6x times x squared minus 1 x, sorry, jumping the gun, that's not right, minus 3. So this equals 0 at x equals 0 from this guy, and then at positive and negative roots of 3. So square root of 3. So and x equals negative square root of 3 and x equals square root of 3. By the way, if we look, we're kind of believe in that. X equals 0. Square root of 3 is something like 1.7, so maybe right around here, and then the negative of that maybe right around here. Looks like we kind of get that changing in that kind of cupped down, cupped up, concave down, concave up behavior. All right. This is continuous everywhere, so I'm just going to break it up. Look at the relevant intervals. So we've got 0, negative square root of 3, positive square root of 3. So I've got 1, 2, 3, 4 intervals to consider. And so for values less than negative square root of 3, so something like maybe negative 2, this part's going to be negative. This part will be negative, and the denominator is always positive. So oh, I'm sorry. If it's a greater magnitude than square root of 3, so if it was something like 2, it would be, this would be positive. So negative times positive. Sorry, mixed up there. So it would be negative. Something in between, like maybe negative 1, would be negative times, now it's for sure negative. Negative times negative is positive. Positive. Something like positive 1, 1 times, sorry, positive times a negative is a negative. And then something bigger than square root of 3, so 2 or whatever, is positive times positive. And you can use specific values, that's no problem. Once you're comfortable, you can do it a little bit faster. That's the way I'm doing it. So negative means concave down, positive means concave up, negative means concave down, negative of the second derivative, positive means concave up. So the concavity changes at each one of these. So we have inflection points at each one. And the inflection points are the ordered pairs. So at 0, it's going to be 0, 0. At negative square root of 3, it's going to be negative square root of 3 squared is 9. So plus 1 is 10. So negative 3 square root of 3 over 10. And then positive square root of 3. 3 square root of 3 over 10. So those are the inflection points. Like we said on the previous slide, right about here, right about here, right about here. Something like that in that ballpark. All right. So a very similar approach, a very similar type of thinking that we did with local extremum. All right, last thing, real quick, this is a rule that is honestly not super useful because anytime you're going to do more work to try to figure out the second derivative. You probably just would do it faster with the first derivative test, but we're going to present it. And it doesn't even always work, so that's the other thing. But the second derivative test, the second derivative tells us about concavity. We can use it in some cases to learn about local extrema. So the second derivative test says, suppose we've got a critical number and the second derivative is continuous near C. If the derivative is 0, so that just means a critical number of a certain type, and the second derivative is positive, then you've got a local minimum. What that looks like is, imagine I've got second derivative positive, so it's concave up, and there's my value C. So that's just a way of identifying that it's a local minimum, versus if you had, it was concave down, that would be this condition, second derivative is negative. And that's a critical number, then you've got a local maximum. So it's something you can remember, but honestly we don't use it too often because the first derivative test is going to work. There's some cases where this doesn't work. First derivative test is going to work for you, and you do less work. You don't have to compute a second derivative. So we presented it here. We're not going to do an example because it's kind of neat, but it's not super. It's not as useful as the first derivative test. And so here's the final note. If you've got a critical number, but the second of the type where the first derivative is 0, and it happens that the second derivative is 0, you can draw no conclusions, at least from this test. So it could be local max, could be minimum, could be neither, but you can't tell anything from the second derivative test. So it doesn't even handle all situations. So stick with the first derivative test for local extrema. Use the second derivative to determine concavity and concave upward, concave downward behavior.